Today, we'll be looking at electrolysis, but we will be looking at the basic principles and some definitions in this topic. We will get into the other topics which deals with calculations and the actual discharge, preferential discharge, which takes into consideration the electrochemical series. But for now, we'll keep it simple by understanding the basic definitions and looking at the principle behind electrolysis. So, the objectives that will be covered in this topic will include 1. Investigating the classification of substances as conductors or non-conductors. We will be looking at the differences between metallic conduction and electrolytic conduction. We will be classifying electrolytes as strong or weak electrolytes based on their conductivity. We will look at definitions such as electrolysis, cathode, anode, cations, and anions. And we will look at the principle behind the electrochemical series. Let us begin. Well, first, we must look at substances that are conductors and substances that are non-conductors. If a substance is able to conduct current, it is classified as a conductor. If it will not conduct current, it is classified as a non-conductor or an insulator. Now we have two types of conduction. You have metallic conduction and you have electrolytic conduction. What is the difference between the two types of conduction? Well, metallic conduction involves the flow of mobile electrons. So we are talking about metals. Metals are able to conduct current because remember when we did metallic conduction, you saw that metals have electrons that are free to flow and move. So in metallic conduction, electrons will move, hence it will conduct current. In electrolytic conduction, it now involves the movement of ions. So the ions are free to move. So whereas in metallic conduction we deal with electrons, in electrolytic conduction we deal with ions, namely cations and anions. Cations are positive ions, while anions are negative ions. So if a substance is to be classified as a conductor, then that substance must be able to conduct either electrons or ions. If it does so, then it is classified as a conductor. If it will not allow electrons or ions to flow through it, then it is a non-conductor. How would we carry out that investigation? Well, if you look at this setup here, you'll see that we have two electrodes, and we will define electrodes in due time. So we have two electrodes here, and we have our connecting wires, and we have a bulb here. And here is our power source. Now, if this substance will allow current to flow through it, then it will be classified as a conductor and the bulb will light. If it will not allow current to flow through it, then it is classified as a non-conductor and the bulb will not light. Let's observe. So let us carry out our investigation to check to see if sugar is a conductor or salt is a conductor. Or if the bulb lights, then they will be considered conductors. If the bulb will not come on, then they will be considered as non-conductors or insulators. So here we have our water, and we will start with sugar. So let us pour some sugar into our water to make a sugar solution. We will now use our electrodes to check to see if the sugar will light the bulb. Now here we have our battery, which is our power source. Here we have a bulb, which will give us a signal if the sugar is a conductor or a non-conductor. And we have our connecting wires and our electrodes. The positive electrode is the anode. It's connected to the positive side of the battery. And the negative electrode is the cathode. It's connected to the negative side of the battery. Let's check to see if sugar is a conductor. So here we dip our electrodes into our solution, and there is no flow of electrons or flow of ions that will cause the bulb to light. Hence, sugar is considered to be a non-conductor or an insulator. Now, when we did bonding, you would have learned that sugar is covalently bonded, or it is a covalent substance. Hence, we don't have any ions to flow. So if there's no ions to flow or electrons to flow in the case of metallic bonding, then there will be no lighting of our bulb. So you will hear the term electrolytes, and we'll discuss non-electrolytes with the same thing of conductor and non-conductors. So we will make that link shortly. Let's remove our sugar and remove our electrode, and we will change our substance now to salt. So this is water alone. So let's check to see if the water will light by itself. So as you can see, the water is a non-conductor because our voltage is low. So let's remove our electrodes, and right now we're going to add salt to our water to make salt solution. Now remember that again in ionic bonding, salt is ionically bonded, and so you will produce ions. So let's just move our salt from the container into the water, and now we're going to check now with our electrodes. So as you can see, the bulb is very bright. Why? Because we have free ions flowing in the solution due to the presence of the salt breaking up into cations and anions to form mobile ions. So the fact that our ions are moving around freely, it means that we have electrolytic conduction, hence our bulb is lit. So you saw where when we placed our salt in our water, our substance, that is the salt, it broke down or decomposed, and therefore it will allow current to pass through it. So that substance we will call an electrolyte. So electrolytes are molten or aqueous substances or solution that decomposes when electric current is passed through it. So in this case, our salt solution will be an example of an electrolyte. The sugar solution did not decompose or broke down when the current was placed in the solution. Therefore, the sugar solution is a non-electrolyte. So non-electrolyte are substances that will not decompose or break down when current is passed through it. So let us remember these two terms, electrolytes and non-electrolytes. And we can link them to conductors and non-conductors. So electrolytes are conductors because they allow current to pass through them, while non-electrolytes are non-conductors because they will not allow current to pass through them, whether it be current through metallic conduction due to electrons or current due to the flow of ions. In this case, it would be electrolytic conduction. So we understand now that electrolytes are conductors and non-electrolytes are non-conductors. And here we have some examples of electrolytes. Acids, and you saw where acids decompose to form ions. Salts will also break down, or alkalis will be ionized. So once you ionize, you'll form ions, hence you are good examples of electrolytes. Electrolytes contain ions which are charged atoms, and you know already that when you are charged, it means that you either lose electrons or gain electrons. And once you lose and gain electrons, you form ions. Cations in the case of sodium and anions in the case of OH minus. You saw here where we said electrolytes are molten substances or aqueous solutions. If you are molten, let's say for example, I give you solid lead bromide. Then this here, if I say it's molten, then it will really form liquid lead ions. Because it is molten, no water is involved. And if no water is involved, then it is in the liquid form. And these are the ions that are present in molten lead bromide. So molten simply means the liquid form of the solid. The solid has been melted. Now that we understand the term electrolytes, which is a substance that will be decomposed on the passage of electric current, we can talk about the fact that we have now different types of electrolytes. We have strong electrolytes and we have weak electrolytes. Let us look at some examples of strong electrolytes and weak electrolytes. Do you remember when I told you that the chemistry is a mixture of topics all in one? You can't understand one area without understanding the other area. So you will be looking at acid, base, and salts at the same time. You'll be hearing about mole concept. At the same time, you'll be hearing about electrolysis. This is a very good example because we did acids, bases, and salts already. But here we are talking about ionization of acids, having strong ionization in the case of strong acids or weak ionization in the case of weak acids. Now we're going to link that form of ionization to a strong electrolyte and a weak electrolyte. So if you are completely ionized, then you would be a strong acid if you are an acid. If you are completely ionized in case of a base, then you'll be considered a strong base. So now strong electrolytes are substances that are completely or fully ionized. So good examples of strong electrolytes are strong acids as well as strong bases or strong alkalis. So in the case of sodium hydroxide, it too will be completely ionized to form sodium ion plus hydroxide ion. So good examples of strong electrolytes are strong acids and strong alkalis. So the strong acid or the strong alkali, they are completely ionized. So we have a lot of ions present in the solution. And if we have a lot of ions, the more ions we have, the greater the conduction and the brighter the bulb should be. We will soon investigate that fact. If you are a weak electrolyte, then you are ionized partially. Remember, the reversible arrow is saying that here, this is our reactant and it produces the products ethanoate ions and H plus ions. But because the arrow is reversible, these will now react and combine to form back this substance. And therefore, this part here will now be acting as the reactants and this will be the product in the reversible reaction. So you'll see that we won't have a lot of ions present in the solution. And if we don't have a lot of ions present, then we say that we are partially ionized, which produces small amount of ions. And therefore, the bulb should not be very bright. Again, we will examine this fact with our experiment. So looking at our experiment again, if this is your water, and I'll put my electrodes into my water, and I'm going to add my salts shortly. I'm going to add small amount of salts to use that to explain weak acids. And if weak acids are ionized partially, then it means that we have small amount of ions present in the solution, so the bulb should not be very bright. So let's check by placing a small amount of salt in our water. As you can see, the bulb came on, but it is very dull, it's dim. This would be an example of a weak electrolyte producing small amount of ions. Hence, the conduction will not be very strong. So here's our bulb. Now, if we are a strong electrolyte, then we would produce a lot of ions in the case of HCl or sodium hydroxide. And the more ions we produce, the greater the amount of current that will flow due to ions, and the brighter the bulb should be. So notice and tell me, what do you observe? Do you realize that the more salt that we add, the brighter the bulb is becoming? This is because the more salt we have, the more ions we are producing, and the more ions we produce, the greater the conduction, hence the brighter the bulb. So you'll see here, let's add some more, and you can see the bulb is becoming very bright. So this represents strong acids or strong alkalis that produce a lot of ions, hence the bulb is very bright. Now, let us remove our salt and see what is going to happen as we remove our salt. You see that by removing the salt, we have no more free ions to flow, and if no free ions to flow, no conduction. Again, if you add back salt, now we have free ions, hence conduction, and the bulb will become bright again. So from this, we can look at some very important terms that you will be seeing throughout this topic of electrolysis. So this would represent our electrochemical cell, our circuit diagram, our container with our electrolyte, and so on. So let's look at the first thing, the term electrolysis. Well, electrolysis is the process by which an electrolyte is decomposed by the passage of electric current. So you see where electrolysis is a process, and then we will go into the word electrolyte. Electrolyte is now the substance that will be decomposed by the passage of electric current. So do you see the link between electrolysis and electrolyte? Again, electrolysis is the process by which an electrolyte is decomposed by the passage of an electric current, whereas electrolyte is the substance that will be decomposed on the passage of electric current. Now we see where we have electrodes. Again, the negative electrode is called the cathode, and the positive electrode is called the anode. These electrodes are inert. You will be seeing and discussing active electrodes, but that is for later on. Now our electrodes are inert. That simply means that they are not reacting with the electrolyte. They serve only one purpose, and that purpose is to take electrons out of the electrolyte and into the electrolyte. That is, they are the point of entry and exit of electrons. Since we're on the electrodes, which is your cathode and your anode, let's discuss the salt. Let's say that this salt is sodium chloride. Then sodium chloride would contain the ions sodium plus, which is a cation, and Cl minus, which is your anion. So cations, which are positive ions, will be attracted to the negative electrode, and the anions, which are your negative ions, are attracted towards the positive electrode. So the cation in this case, which is sodium ion, will be attracted towards the negative electrode, which is the cathode, and the negative ion, which is Cl minus, will be attracted towards the positive electrode, which is your anode. We will be discussing migration and preferential discharge, but first we must have an understanding of the electrochemical series. Let's recap the terms and then we will go into the electrochemical series. So here are our terms. Electrolysis is a process by which an electrolyte is decomposed by passing electric current through it. Again, the electrolyte now is the substance that is decomposed on the passage of the electric current. The electrodes are your inert rods, and examples of your inert rods are graphite or platinum. And again, we say that these are inert electrodes. Your cathode is your negative electrode, and electrons enter the electrolytes through the cathode. The anode is your positive electrode, and electrons leave the electrolyte through the anode. Because electrons are being accepted or enter at the cathode, we're going to say that the process that takes place at the cathode is reduction. And you would remember from oxidation and reduction that reduction simply means the gaining of electrons. Whereas at the anode, the electrons are leaving, so electrons are lost at the anode. Therefore, we have the process of oxidation taking place at the anode. So we always have reduction taking place at the cathode, and we always have oxidation taking place at the anode. Again, reduction takes place at the cathode and oxidation takes place at the anode. The cations are your positive ions, and they are attracted towards the negative electrodes, which is your cathode. Remember that cations are positive ions in the case of Na+, and they are attracted towards the cathode, and the cathode is your negative electrode. The anions, again, which are your negative ions, are attracted towards the electrode that is positive. So opposite charges attract. So cations are attracted to negative electrode, while anions are attracted to the positive electrodes. So here is a very simple setup of our cell. And the cations and the anions are freely moving about in the container. But the moment that the current is turned on, you'll notice that the negative ions are attracted towards the positive electrode, and the positive ions are attracted towards the negative electrode. We call that migration. So simply put, migration is the movement of ions towards their respective electrodes. So once the current is turned on, if you are a cation, you'll move towards the cathode, negative electrode. If you are an anion, negative, then you move towards the anode, which is your positive electrode, and that is migration. Once the ions are there, the next thing now would be which ion, because you're going to have more than one ions moving towards the anode and the cathode, but which one will be discharged in preference to the other. Before we can explain that, we have to look at the electrochemical series, and then we will discuss the factors. Let's have a look at the electrochemical series. So basically, the electrochemical series will be used to predict preferential discharge. And when I say preferential discharge, I mean which ion will come off as an atom, which is your element in its free state, or a molecule in the case of a gas. Now, the electrochemical series is simply a list of metal ions. Now, please do not confuse the electrochemical series with the reactivity series. The reactivity series is different from the electrochemical series. The reactivity series is a list of metals placed in order of reactivity, having the more or the most reactive metals at the top and the least reactive at the bottom of the series. That is not to be confused with the electrochemical series. The electrochemical series now is a list of metal ions as well as non-metal anions. So we have metal ions or non-metal ions, and they are placed in order of reducing and oxidizing ability. So the cations here are your metal ions, and the anions here are your non-metal ions. The cations are all positive, and the non-metal, they're all negative. Now we say that it is a list of cations and anions, and they are placed in order of reducing and oxidizing ability. So the first thing I want you to understand is this. For the positive ions, which are your cations, they will be reduced. In other words, on this side of the table, we will be looking at their reducing ability. In other words, which one will be reduced easier than the other? The one that will be reduced more easily than the other is the one that will take less energy. And so we will be discussing this part shortly and looking at each of these ions and what we mean by reducing ability. On this side, which is your anions, they will be oxidized because they are losing electrons, and therefore we will be discussing oxidizing ability. So in terms of cations, we must discuss reducing ability. In terms of anions, we must discuss oxidizing ability. Let's write some half equations for our metal cations and metal anions. So, in order to write the equation and explain preferential discharge, we must understand the trend in reducing ability for the cations and the trend in oxidizing ability for anions. So in terms of the cations, we will say that reducing ability increases down the series, while oxidizing ability increases down the series. So, reducing ability increases down, while oxidizing ability increases down the series. What am I saying? I'm saying to you that remember that positive ions, in order to form their atoms, they must gain electrons. That means that they will be reduced. So, I will explain that based on the accepting of electrons, while for the anions, I will explain that based on the loss of electrons. Let's look at a few of these. Let's look at, for example, sodium ion, which forms sodium atom. Let's look at zinc 2+, which forms zinc solid. And let's look at hydrogen H+ ion, which forms H2 gas. And finally, let's look at copper 2, which forms copper atom. In terms of reducing ability, all of these positive ions will be reduced because they are accepting electrons. Electrons are gained here. So this is +1 electron to produce sodium atom, +2 electrons to produce zinc atom, +2 electrons because I must balance this to get mass balance and charge balance. And here I'll add 2 electrons here. But I am saying that copper is more easily reduced than, say, zinc or sodium. So reducing ability in terms of copper, it is more easily reduced than hydrogen, than zinc, or than sodium. So as long as your positive ion is lower than the other ion present, then the one that's lowest will come off in preference to the one above it. Why? Because it is low in the series, it means that it is more easily reduced and therefore takes less energy and will be preferentially discharged. In terms of your metal anions, let's start with chlorine, and I will write Cl-, and of course that will form Cl gas. Br- will form Br2, and let's go straight to OH-, that will form water plus oxygen. Now remember that electrons are being lost on the anion side. So let's do our half equation. Let's balance the mass first and then we'll balance the charge. So here I'll put 2 here to balance this 2 here. And if I have mass balance, in order to have charge balance, I must put 2 electrons here. You will remember that we say that as long as it is oxidation, then the electrons are placed on the right, which suggests that electrons are being lost. Now I have 2 minus on my right and 2 minus on my left. I am balanced. The same thing for Br, which would balance out both mass and charge balance. Now in terms of hydroxide, which is the lowest in the series, you'll notice that whenever hydroxide ions are present and they form their molecule in its free state, they form water and oxygen all the time. So OH minus will produce water and oxygen. Now we must balance this equation because in terms of mass balance and charge balance, it is not balanced. So to balance this, I have 2 here. So I'll put 2 here. But I'll notice that if I put 2 here, I won't balance my oxygen. But if I put 4 here, I'll now have 2 times 2, 4 hydrogen. Now I have 4 hydrogen here. So my H is balanced. Now I have 4 O's. I have 2 O here and 2, that's 4 O. So my mass is balanced. What about my charge? I have 4 negative ions on the left-hand side. So to balance that, I must have 4 electrons on the right. So these are all oxidation equations where electrons are lost. While on the cation side, these are all reduction equations where electrons are gained. On the cations, reducing ability increases down the series. In terms of anions, oxidizing ability increases down the series. This explains oxidizing and reducing ability, which explains preferential discharge. Now we can start looking more deeply now on the factors that determine preferential discharge. But that will be done in the next topic, which we'll be looking at the electrolysis of substances, identifying the 3 factors that are responsible for preferential discharge. See you then.